we sent some summer funding down to UNO for 3 graduate students, and Brad was one of the PhD students there at the time, and he stood out above the rest. So after that little summer internship, we invited him to come finish his PhD on our project, this Wavelet project he's going to start today. And in about a year, he went from absolutely nothing to a huge 100+ page dissertation that he successfully defended, I think, at the end of 2023.
Yes.
So that was awesome. Then we brought him on as a postdoc here, and he took that dissertation and turned it into a peer-reviewed article that was just published this year.
Mm-hmm.
And he just also published a book chapter. The original work was on just SST, and he extended that work to using the Wavelet transform for SWOT, simulated SWOT data specifically. He's going to talk about that today. So he's on fire, cranking out the papers. So we're very proud of him, and we're excited to hire him on as a federal employee here when the hiring freeze ends, hopefully soon. And so we're very grateful that you guys have given us the chance for him to share his work here today. And with that, I'll hand it over to Brad.
Thanks, Joseph. So yeah, like Joseph was saying, I'm going to be talking about wavelet ocean data assimilation, specifically with 3D VAR. The first set of stuff I'm going to be showing is mostly dealing with SST observations, and then the later half is going to be with simulated SWOT observations. So to get started, kind of give some relevant background on the kind of thing that we're trying to tackle here. If we have a full field SST observation, like I have shown here on the left, actually, let me do the laser pointer. That would be helpful. Let's see, is that coming through? Should be, I think so. Okay, so yeah, like we have here on the left, we have data everywhere in the open ocean. We have land here. This dense data set here comes with some potential problems. It either has redundant small scale information, or it has overly correlated observational errors. And in operational sense, at least here at NRL, and I'm sure a lot of other places, we solve this using super observations. And what a super observation is essentially you take a circle. This is kind of simplifying it, but you take a circle of some radius. In this example here, that radius is 30 kilometers. You average everything within that radius, and you keep that centered average point. So you go from a field of about 1 million data points to something about 1,000. And this kind of leaves you to correcting in your increment or in your analysis only large scale information. So you had a lot of small scale stuff that was here that's essentially filtered out here. And so today, our hypothesis is that with wavelet-based assimilation, we can perform the same necessary functions here, reducing the redundant small scale information and reducing any potentially correlated observational errors, and still perform, and do so more accurately and efficiently compared to super ops. So we can do the same thing as super ops, but a bit more accurately and a bit more efficiently. So what is the wavelet transform? Not a lot of people are familiar with this, but more people are familiar with its, I guess you could say, cousin, the Fourier transform. And the Fourier transform is when you take a signal and you kind of represent its frequency information or its spectrum. The wavelet transform is doing the same thing, as you can see here in the continuous form. You kind of take a mother wavelet, this function here, and your signal, and you essentially are stretching and scaling the mother wavelet as you kind of convolve it with your signal, and you kind of get this representation at different scales and shifts. So it's kind of representing the scale and shift, which is kind of analogous to frequency content of your signal. And then since we were working with discrete information, we went with the discrete wavelet transform, which is kind of organized as a filter bank. So it's a set of low pass and high pass filters. And so you can do these at different levels, which correspond to the different kind of scales on the left side over here, but in kind of a more discrete step-wise way. And all you're doing is you're convolving with these low pass and high pass filter coefficients that correspond to a particular discrete mother wavelet. And then you are downsampling the result to kind of get these two distinct outputs at each level. You have an approximation output, which is going to be here, and you have a high pass output, which is called the details. So kind of dive a little bit more into the discrete wavelet transform in the 1D case. And so you have these discrete mother wavelets, which these themselves are actually recursively defined from the coefficients, because there's not a nice closed form of these functions. You have to kind of define them from the coefficients themselves to kind of get a representational graphical output of them. But a kind of good rule of thumb is once you can get this representation, is like the correct choice of mother wavelet for your application is the one that kind of best represents the features that you're either trying to extract or just has the most similar features like this is seen in your data. So that's kind of just a rule of thumb with the wavelet transform. So specifically for doing a 1D transform is that this was your signal input, just as an example. When you do one level of transform, you get this output here. You have your approximations, which is 4, and you have your details, which is 4, where the original was 8. So you see you kind of split it up and then half each one. So now they're each a half the size of the original input. This is corresponding to your large scale, low frequency information, and this is your small scale, high frequency information. And the way you can think about this, if this is your frequency content of your signal, the details is corresponding to a kind of bin going from here to here across all of these. You have to kind of imagine it. And then the approximation, this would be your details on this side. Sorry, I had that backwards. And then your approximation would be this one here. So corresponding over across the whole low frequency, and this would be corresponding over across all your high frequencies. That was one level. You can do a further level transform to go to a second level, and you take your approximation as input now and do the same transform again. So you convolve with the same low pass and the same high pass filter. And then you get these output now. You now get a new approximation coefficient, a new second level detail coefficients, and the same original first level detail coefficients. So now you can imagine we get this box now at the second level. We get this box at the second level, and we have a new approximation that would be covering here. And then you can go one more again, further split this in half at level 3. And now we would get this graph here in full as it is. You have your approximation at the end here, your detail level 3 here, level 2, level 1. And so as you can see, what that is essentially doing is taking your signal and splitting up its frequency content into different bins of, and these bins are getting smaller and smaller in size as we go on. It's kind of this multi-resolution kind of approach here. So we were working with 2D discrete data, so we needed a question. Oh, I thought I heard something, but okay. If you have a question, just feel free to ask. So here we have the 2D transform, and the way that is done is essentially you do a 1D transform across the rows. I'm sorry, down the rows and then across the columns. So we go like this. We get one kind of 2 regions of output here. We have our low pass output, our high pass output, and then you do another one down, and now we end up with 4 regions here. We have our low pass, our low pass, high pass, low pass, high pass. And these have the name when you actually get the output from this was, if this was the input here, this output would be the wavelet output. We have our horizontal details, which is the low pass, high pass, our vertical details, the high pass, low pass, and the diagonal, which is the high pass, high pass. And then we have our approximation, which is the lowest of the lowest frequencies in our signal. And you can kind of get why these have these particular names. If you look very closely, you can see that this has horizontally shaped details here, and this has vertically shaped details, and this kind of has like diagonal, which this one's a little bit harder to see. And this approximation is essentially just a smooth approximation of your input signal. Excuse me. And then if we want to do another level of transform here, we take our approximation region here and do the same thing again. So we get this kind of cascading effect. And you can keep going and going and going, further splitting into more and more bins. So how do we plan on using this with 3D VAR or just in data assimilation? Well, we can take this approximation and remove all the details and assimilate this as our observation. So this will allow us to have a naturally multi-scale and one assimilation step because we essentially have filtered our observation to remove the unwanted small scale information, but we still do have some small scale information because of the level that we transform to. We haven't removed all of it, right? So we're keeping within a certain bin here. And this also allows us to kind of have a size reduction in wavelet space. This is going to be 1/4 to the level because each time you do a one level transform, you're downsampling by half. So you're removing half the data in that dimension, half the data in this dimension. So that corresponds to this size reduction here for the approximation coefficients. And we say that this is going to be able to preserve observational information because we have a inverse transform, where super obs do not. So if you remember, super obs would be kind of these discrete points on the model grid, be about 1,000 data points, and then you have a lot of decimated areas around there where there's no data from compared to the original dense observation. But when we do the inverse transform on just the approximations here, this is the field we get, right? So we get this inverse that has data now returned to the full model grid. We have data everywhere, albeit it is just now filtered to remove that kind of potentially correlated small scale observational errors or redundant small scale information. And then when we take the difference of this to our input, this is what we get. And you can see we kind of have an expected amount of details out in the open ocean removed here, but there is a lot of errors along the coastline you may be noticing. And this is a known issue with wavelets, are really just discrete convolutions in general, called edge effects. So when you have a discrete convolution, convolutions are assumed to be continuous in space. So when you reach the edge of something, you're now convolving with zeros or nans or something. So you're getting these distortions on the edges. You can fix this by doing either like periodic extension of your signal or kind of circular extension or some kind of extension method. And the one that we went with here is periodic extension, but as you can see, you still are left with some edge effects here. There are ways to completely remove this, but those are kind of special circumstances. And so in general, you kind of have to kind of use the best extension method to kind of live with them per se. Okay, so now we actually are looking at the wavelet 3D VAR. So we're incorporating the wavelet transform into the 3D VAR analysis equation up here on the left. We have our analysis, we have our model background, X of B, we have our background covariance operator B, our observational operator H, and our observational covariance, observational covariance operator R, and our observations Y. So to do this now with wavelets, we are essentially bringing this equation into wavelet space with the help of our wavelet operator W. So we will calculate our innovation in wavelet space. So we have the Y prime here means that the observations are now in wavelet space. And then we will bring our model background into wavelet space with our wavelet operator. So it's going to remove the same level of details, perform the transform to the same level and all those things to make sure that we're in a compatible wavelet space. But there is one caveat here, is that the observations in the model background need to be on the same grid prior to transforming. And that's because these coefficients, when you perform the DWT, or the discrete wavelet transform, it's really a linear projection onto these spatially localized basis functions. So if you were to transform them on different grids, they would both be in wavelet space, but they won't be quite compatible. So to make sure they're compatible in wavelet space, we put them on the same grid prior to transforming. And this grid can be some, secondary grid that you might have that you can put both the observations and the model background on and then do the transform. But what we chose to do was just put our observations on the model grid. So we interpolated our observation to the model grid and then took the transform, and that's what y prime is. And then we just took the Wavelet transform of our model background, which is already on the model grid, and then those are both brought into Wavelet space. And it should be noted that for these particular SST maps that we were using here, the traditional observational operator H was just identity, because it was just already one-to-one where everything was. There was no need to specially map anything from one space to another because they were both compatible already. So after we get our innovation in wavelet space, we will then compute our innovation, our increment using the conjugate gradient method. And the picture I've shown here is essentially before post multiplication, but back on the model grid. So after we saw the conjugate gradient, we've kind of come out of it. We go back to the model grid, but we haven't post multiplied yet. So that's the images here. And you can see compared to superobs have a lot of sparse data, right? It's just those points, whereas the wavelet at this point in time has this kind of spatially spread out information, and it's, has a lot of details still in it. So there's just a comparison of these two at this similar point in time of the solving for the increment. Finally, we post multiply by the background covariance operator, which will smooth out the field to its correlation scale, which for both the superobs and the wavelets, the results I'm going to show, this correlation scale was similar, which is roughly about 30 kilometers on average. Okay, so just a little bit, maybe more background on why this is working or how it's working is that for the conjugate gradient method, when you're doing the matrix inversion, right, we're working with this equation here, specifically for the wavelets. But if you're working with just superobs, it would just be the, without W's here, just be HBHT plus R. The more this is kept diagonally dominant, the A here, the faster the conjugate gradient converges. If you have a lot of significant off-diagonal terms in this matrix, it may not even converge. You may, take, or it may take forever. So we want to do things to make sure that this is diagonally dominant. And so we typically assume observations are uncorrelated. So that gives us a diagonal R here. So we don't really have to do much there because it's already diagonally dominant. So what we can do is we can kind of manipulate this part of the equation here. And the way we do that is with superobs and wavelets. So the superobs will kind of enforce, and now the wavelets will enforce this kind of diagonally dominant nature by removing significant off-diagonal terms, which is typically these small scale, overly correlated things. And for example, you can see that happening with the wavelet is if we have our regular SST observation, this is the PSD of that and the dashed line here. It has power everywhere, even at these really small scales. This is like 10 kilometers and under. But when we take the wavelet transform of that, when we remove the detail coefficients and then inverse transform back to the model grid and take the PSD, this is that spectrum here in the solid. So you can see now we've removed essentially this 10 kilometer and under information. It has essentially the power going to zero now. But we still have some important small scale information that we want to assimilate from here on up, which is around 100 kilometers to 10 kilometers. So removed potentially problems that would cause significant off-diagonal terms, and we kept stuff that we would want to assimilate. And one final thing about the wavelet method is we had to account for the variance. The superobs are performed to this footprint here on the model grid, but wavelets are now at a per grid basis. So our variance needed to be, needed to be a part of that, or need to be modified to include that. So what we do to get our per grid variance is divide by the footprint of the superobs here. So that means that now our wavelet variance and superobs variance that we did in these experiments are kind of more apples to apples. It's just that we had to kind of deflate the wavelet variance because it's represented as such a smaller footprint compared to the superobs. And like I was mentioning before, for the SST case, our traditional observational operator was identity. It just didn't have to do anything. But now in the more generalized case, when you don't have observations everywhere in the open ocean, and you might have, for instance, like these SWOT tracks, now edge effects might be a problem. So what we did is we used the observation operator H here to essentially enforce ob-to-ob correlations. So we mask by the original observation locations on the model grid. So we're only keeping the observations where they are themselves, and everything else would just be zero. So when we transform with the wavelet transform, we're just transforming the observations themselves. So it kind of, and then when we come back with H here, when we come back to the model grid, it's enforcing just those locations, and we're not keeping any outside edge effects that might have popped up when we did this. All right, here's the experimental setup for the results I'm about to show. We had a nature run, which was run for a few months using NCOM and ENCODA, which is the Navy coastal ocean model and the Navy coupled ocean data assimilation. This was run until December 2019. We then copied that state, gave it to NCOM at December 2018 with the forcings and everything of December 2018, and ran that forward 1 month with no DA. That produced our background state for our twin data assimilation experiments. And then we used observations sampled from the nature run at each 00Z to kind of drive these experiments towards the nature run. So we're able to kind of derive error results from the nature run that we have here for each of these experiments that run out from here. We used NCOM as our forecasting model, and we had Gaussian correlation operators, both horizontal and vertical, for all these experiments. The vertical one was when we produced our increment. It kind of just spread our surface increment down to the mixed layer to kind of give us a 3D ish increment, and we cycled each one for 6 months. And if you were curious, this was the difference from this kind of delay here, this kind of seasonal delay, our yearly delay, I'm sorry. You can see that they're pretty much both similar looking, but different enough that we can use DA to kind of bring this state to our nature state. All right, and here's those results. So all that to show that we have a free run and we have our super obs wavelets, but they're basically on top of each other. So this at first was a pretty disheartening thing that when we first saw it. Our wavelet run in blue here and our super ob run in dashed. The wavelets are just ever so slightly outperforming the super obs, but we realized that the correlation scale for the background covariance operator might be what's the issue here, because the correlation operator is at Rossby scale, which is what the super obs were made at, which is roughly the 32 kilometers on average. But the wavelets, when we, since we're taking just the approximation coefficients, we're essentially just using that low pass filter of the wavelets so we can look at its PSD and figure out the filter cutoff. So since we were doing a level 3 transform and keeping just those approximations, that corresponds to a cutoff of about 13 kilometers. So that means is that with our wavelet increment, we were having information from 13 kilometers and up. Everything 13 kilometers and below was being removed with the wavelet method. But then we were post-multiplying with the background covariance operator, and that was smoothing everything to 32 kilometers. So this wasn't a problem for super obs because super obs were made already at this correlation scale. And so when you smooth it out, you're kind of just enforcing kind of what it's already at. But with the wavelets, we're wiping out everything from 13 to 32 kilometers. So we're removing kind of the advantage that wavelets had. So when we allowed the post-multiplication to be at wavelet scale for the wavelet method, these were the results we had here. So you can see now we're now retaining a lot more of that small scale information in the post-multiplication. And compared to super obs here, the wavelet method is outperforming it now. So this was allowed to be at its natural wavelet scale. Another experiment we did was that we added some simulated clouds using Perlin noise to kind of see how the edge effects might be a problem, if they are. And you can see kind of from this kind of daily show here that really the errors that we're seeing are just the kind of expected errors that you would get from having clouds in your data. It's just large errors. So the difference from this, the dashed line is the clouded and the solid is the not clouded, but they're both wavelet scale. It's not that great. The difference isn't that great. So the addition of these clouds and maybe the addition of error from these edge effects maybe does not play that big of a role, but further testing of that may be necessary. And so this is the paper that we published with this SST only assimilation and everything I just talked about. Now we're going to look at the assimilated SWOT stuff. It's the stuff that y'all should be more interested in. So we used a QG model. This is kind of get away from the problems that might come with working with a free surface model and assimilating SSH observations directly. So we wanted to just focus on just the wavelet method with SSH. We didn't want to have to deal with potential introduction of gravity waves or things like that. So we went with the QG model, and then we used a SWOT simulator and sampled our nature run of those lat longs given by the SWOT simulator to get our SWOT tracks. And here's that experiment to set up, is that we had a QG model that was run for 5 months with no DA. That gave us 2 background states here for our twin data assimilation experiments. And then to kind of get our observations that we sampled from a nature run, we let this background state run an additional 2 months with no DA again. And then we sampled the state here as if it was this day here. So kind of like this 2-month lagged nature run is what we used for our observations. This was a 2-kilometer horizontal resolution only. There was no vertical in this because it was just the 1.5 layer QG model. And then we assimilated only SSH observations sampled from the nature run, every 0,0C. We had just a horizontal Gaussian correlation operator, and we again cycled for 6 months. So now this is the results here. And you can see we have the Rossby scale experiment, a wavelet scale experiment, and a super obs. And the Rossby scale and the super obs are basically on top of each other. But the wavelet scale has higher error until about day 32, when it finally overtakes both of those. And again, this was another disheartening result, and we were wondering what was going on. And then we kind of did some more thinking and kind of realized that because of the localized nature of the SWOT tracks, and we're modifying the wavelet scale correlation length scale, it's not spreading the increment out as much off the swath compared to the other two, the Rossby scale and the super ob. They're spreading their increments out more. But the wavelet scale is making a better localized correction compared to the other two. And you can see that when we look at the RMSE of just where the SWOT tracks themselves were. Because this what we're calculating here was the RMSE globally, or in this whole region. And that's what we have here on the right. We masked by the observation locations and computed the RMSE for that. And you can see from the start that the wavelet scale in solid blue here is doing better compared to the other two runs. And then it just gets even more better as the run goes on. So because of the smaller correlation length scale, we weren't spreading the result out away from the swath as much. So it takes a while to catch up, about 32 days or 33 days here. But once it does catch up, the increment is consistently better. So you're just getting this better localized correction for the sacrifice of maybe not globally not reducing your error as fast. And so this is the book chapter that we just recently got accepted for publication, and it's going to be published sometime in February or March in the Data Assimilation for Atmospheric, Oceanic, and Hydraulic Applications, Volume 5. If you are curious, you want to keep up on that, you can maybe just email me, and I can email you back when it comes out, or send you a link, something like that. And so yeah, that's it. So we have this in summary, we have that our wavelets, they're naturally multiscale with one assimilation step because we are keeping just those approximation coefficients and removing all of our details. Then this is also going to preserve more observational information compared to superobs because we have a inverse transform that can return us back to the full model grid. Yeah, so thank you. If there's any questions, please let me know.
Thank you. Questions for Bradley?
Everyone understood completely.
I had a bunch of questions and some of them you answered. So.
Good.
I guess
I have a question.
Yeah, go ahead.
Thank you, Sarah. Thank you for these amazing presentations using wavelets for such kinds of mapping the varieties. So I have a questions. Are you taking in considerations all the spectral components provided by the wavelets, or are you taking just the spectral components with a higher variance?
So we're not really distinguishing like what we're keeping in terms of the approximations, but we are removing all the detail coefficients. So like we're keeping the whole approximation coefficients that are, you know, the output of the transform, and then all the details get removed. So there's no like thresholding happening where we're like keeping a certain threshold of like, you know, as you would typically with wavelet transform and like compression and stuff. You do like either soft or hard thresholding to keep a certain percentage of your detail or approximations, but we're just removing everything. We're removing all the details and just the approximations. Is that?
Yeah.
Okay.
Yeah. And are you using this approach for all examples, or it depends on the size or the process?
So the level of transform in what mother wavelet to use is kind of the only I guess you can say like knobs that we're turning here. So depending on what level you transform to, the changes kind of what that, as I was saying, like that. Oops, how can I go? Here you go. Too far. Here we go. So depending on what level you do and what mother wavelet you choose depends on your kind of changes your filter cutoff here. So if we were to do just one level, that might not be enough to remove any potential small scale correlated things. So this is kind of our knobs that we change here. Is we, you know, kind of depending on the data or the observation, we might have to do either maybe further levels of transform, or maybe choose a different mother wavelet that would give you slightly a different spectrum here. So that's kind of what we change there.
Yeah. Thank you.
Mm-hmm.
Luciana, go ahead.
Yeah, I have a question. You mentioned at a certain point in looking at these figures that near to the coast you have a problem with the wavelet.
Mm-hmm.
Yeah. So what does it mean? That it's better, the methodology is good only in open ocean, or that something can be done in order to not be disturbed from the coast?
Yeah, so there are kind of signal extinction methods you can do. Like, you know, you can periodically pad your signal or things like that. That kind of mitigates it a little bit. But the biggest thing that we probably did to mitigate it, let's see if I can get to that slide. Actually, yeah, right here. So with things like SWOT tracks, these are considered edges on our observations. So these are going to produce edge effects at these edges. And so we overcame that by enforcing to keep only where the observation itself originally was on the inverse transform. So essentially, if there were edges out here, they're no longer retained, right? So that was one of the ways we kind of dealt with that. But so you can kind of deal with it in the open ocean. But the ones that might have popped up, like right here, for instance, close to the coastline, those would have been in the final result, and they kind of would have affected negatively the result here. And that's when your signal extension methods might help you there. So like along the coastline might hurt, but it's really just going to be like maybe sometimes 2 or 3 to 4 grid points away from the coast that error pops up. It really all depends on the kind of like the level of transform and all the stuff that you do. Because the further levels you do, the more that edge effect gets amplified.
This is you put a buffer along to the coast of 20 kilometer or something like this?
Yeah, that could be a way you can deal with it. You can kind of just throw away everything along the coast, yeah. So that like if the error gets too bad, then yeah, you can kind of just mask it out, similar to how we're doing here. Yeah, that could be a way to deal with it.
Thank you.
Thank you.
Bradley, you showed a twin experiment from, and if I understood, it was pre-SWOT.
The SST one, yeah, that was I think SWOT was out at the time, but we started with oops, I went too far. We started with SST because that seemed like the most straightforward way to kind of prove this that it works. So yeah, this was a setup that I got from Joseph. Actually, he had a nature run, and then I kind of used that to perform the twin experiments.
And then when you do the SWOT, did you do actual SWOT data, or was it just from
it was from the SWOT simulator.
It was from the simulator.
Yes.
So have you thought about trying it with SWOT data?
It is something that we want to pursue, and it's something that's coming up in the pipeline.
Yeah, I imagine that would introduce new adventures.
Yes. Yeah, so far, I guess I should have really prefaced that every experiment here was like kind of simulated, fully simulated. I haven't really worked with real observations yet, so it's something coming up soon.
What do you anticipate the issues to be?
I think with the real data, determining what actually leveled to go to and things like that. So like what to actually remove or is that what to filter exactly would be the kind of biggest thing to go about. But yeah, and I'm sure there's gonna be other problems that pop up that I can't foresee yet, as is the nature.
I think the scariest thing that he's dealing with right now, you are starting to do a 40VAR experiment with SWOT data.
Yes.
And the main reason for skipping using NCOM for the SWOT data in this one and using the QG model is the 3D projection. So the Wavelet transform is a 2-dimensional transform. So the way we usually do it in real life operationally is to make those ISOP profiles, those synthetic temperature and salinity profiles. So how do you do like a multi-level decomposition of the profiles? That doesn't seem great. So we kind of skipped ahead to 40VAR and we're using it as kind of the H operator in there and then allowing the 40VAR to come up with the 3-dimensional component on itself.
I was going to ask next about prospects for 40VAR. So
already in the
but you have it. Hans and him are working hard on that, but it's not solved yet, right, Brad?
Yeah, still working on it.
Next seminar, see you in 6 months.
Hopefully.
Yeah, well, we've been having our own adventures, which Ariane will talk about next month.
Good.
Someone had a question, I think.
Yeah. Sorry. Thank you for this talk. I have a question about this extension to the 40VAR. To what extent is it possible to include the time dimension in your wavelet decomposition? Like to have like a time decorrelation scale so that you can use multiple observations to constrain one component? I think for SWOT and like along track data, if you mix all kind of observation you can have of the sea surface, it can be relevant to think about the time dimensions.
So the way we're currently thinking of pursuing the time dimension with the 40VAR is essentially we're taking like different snapshots of the observations and transforming each of those snapshots. So we're getting like these maps of these different snapshots and transforming them and then assimilating them kind of at their corresponding times with the 40VAR. that is the way we're currently thinking about it, but there might be a better way there. But yeah, the transform, the way we transform, at least as far as I'm used to it, is mostly a spatial transform.
Yeah.
So incorporating both a spatial and time component to it. I'm sure there might be a way. I'm just not.
Yeah, actually,
familiar with
you
it.
can easily say that one component of one spatial scale has like a time envelope, and so you can like state that the small scales high frequency in time and large scale are large frequencies, so that you can reduce your
Yeah.
number of degrees of freedom like this by prescribing like a law between time and space, and this is actually observed from altimetry, and like you can deduce this law. So like this is done, for instance, in the new drugs product, like the algorithm MIOS from Clément Hubelmann, and he's doing like wavelet analysis for mapping the sea surface height. And I think it's not as theoretical as you do. I think it's more like made with the hands, but I think it's
Gotcha.
a good way to have ideas. I think to include the time dimension.
Gotcha. Yeah, that's very cool. I'll look into that. Thank you. Yeah.
So, Florian,
Yeah.
one of the difficulties to do to extend to the time dimension with observations like SWOT is that you have compared to the space dimension, you have a very low frequency in time, right?
Yeah, sure. Yeah.
So these SWOT tracks are coming maybe once every 12 hours in a domain, or smaller domains, you may have a track maybe once a day or less. So
Yeah.
that's the problem for extending it to the time dimension. But the
Yeah,
40
but if
bar has
you
sorry.
No, yeah, I just wanted to say, if you include also all the conventional constellation, like the 5 or 6 or 7 altimeters, even if they look in one dimension in space, if you like use the synergy with SWOT that's observed in two dimensions, then you have like kind of a full picture. Because yeah, if you like include all the satellites, all the altimeters, then you have a better time resolution than if you just use SWOT alone. So it might be a way to use all the altimeters at the same time. SWOT gives the high spatial resolution, and the conventional altimeters are here to bring the time correlation between observations.
But do we need that for the 40 var? Because 40 var by itself already includes the time dimension in the state space. Here we're only talking about the decomposition of the observations. So
Yeah.
as long as we have observations coming in time, even though we don't apply the wavelets in time, we're still accounting for all the observations.
Yeah, I see. Yeah. But actually, with the 4D you are limited by the like what you would do. I think it's estimate an initial condition and then have a forecast of the model. It's what you do. But I think with the wavelet, the analysis could have like an, how do you say that in data assimilation? Like a when the model is not perfect and you can estimate some errors of the model in terms of fluxes, and so this flux, like these error fluxes, can be projected into the wavelet basis. Also, that's also it's a way to correct in time and space the model trajectory, fitting the observations.
Gotcha.
I don't know. It's like ideas like this, but
Oh, okay. So it seems like you're saying we can use wavelets as their own analysis tool,
yeah,
not necessarily as the observation operator for 40 var.
exactly. Yeah, actually, you
Okay,
can do
okay.
all
I get
the minimization process in the latent space, like as they do with the machine learning techniques, but it's kind of the same with the wavelet basis. You use like it's a latent space where you can perform your optimization in this reduced basis, which is wavelet.
Yeah. So I mean, we can look at this as an interpolation problem, right?
Yeah.
So if you only look using wavelet as the analysis tool, then you have to provide what connects the observations from one side to the next side. uh, outside of the dynamics of the model. So what Fodivar brings in the analysis is that you actually have a dynamical model that propagates information from one point to the next.
Yeah. Yeah. Yeah, but still you can say that the model is not perfect, and you can estimate also the corrective fluxes, and these fluxes can be projected with the wavelets.
Yeah,
basically.
yeah, sure.
Yeah, so that you have the full. But yeah, we can maybe discuss about that later. But like if people have other questions. But yeah, I think it's a nice discussions. Like I think like bringing wavelet in the conventional data estimation techniques are it's very nice.
Yes.
Other questions? Bradley, can I ask about the mother wavelet? You said that that's a choice. What have you tried? What works best?
So
how much do you actually tweak the mother wavelet?
So currently, this was all just kind of a proof of concept. So we really only have tried one mother wavelet that was previously tested before I got here. That there was some tests done, as I understand, to kind of determine which one was the best one. So we really just tried the Debussier's 8, the DB8, as we would call it. But there is a whole lot of other wavelet families out there. They are, as far as I know, easily accessible, like in terms of like if you're using like Pi wavelets, which is like a Python wavelet library. They have, I think, 52 mother wavelets in there. I myself, in our little local Fortran wavelet transform library that I did is this. I kind of copied the same mother wavelets from there. So we kind of did the same 52 of them, or 40. I think we actually know 48. I think I'm misremembering the number here. So yeah, there's more. There's you can always make a new mother wavelet, but essentially the properties that are associated with these is essentially the more points that you have, and the more filter coefficients you have in your discrete transform, the more kind of complexity you can represent in your signal. And that essentially just boils down to like that picture I had up earlier. You can't, in terms of our application, it's really the choice of mother wavelet is going to change how this looks. And then the different levels from that, you can then determine kind of what your cutoff you want it to be.
How does the cost compare for the wavelet approach versus the traditional super obs?
So we didn't run extensive timing tests, but from the little bit of testing I did do, it does seem like they're at least comparable in terms of how long it takes to compute. There was a certain time test I did recently where I had the super obs cycle for one day and the wavelet cycle for one day. And from that test alone, it did look like the wavelets ran just a little bit faster. But the thing we're not accounting for that is that the super obs were actually, they're essentially computed beforehand, right? You kind of make your super obs and then you do your assimilation. Where the wavelet method, I'm doing my both forward and inverse transforms within the assimilation method. So the timing kind of gets a little wonky there, but for the most part, generally from like kind of a wall clock standpoint for the whole thing, they're not totally different.
And I have one more question if nobody else does. You mentioned about trying to get the matrix you invert to be diagonally dominant and playing with R and the wavelet structure to make sure that that's happening. And I think one thing that struck me is that if you assumed all your data to be statistically uncorrelated random points, and you subsampled them, if you did a really cheap super obs and you just took every 10th point, for example, you would guarantee that the data were uncorrelated, and that would be really good for diagonal dominance. When you use the wavelet, you are actually allowing the points to be correlated, which could interfere with this desire for diagonal dominance. So I'm hoping you'll explain how that really works.
So, as far as I understand it, when we are keeping just those approximation coefficients, we're throwing away those details. So those are the things that those are the terms or components of the signal, if you will, that should be correlated. So when we remove those, we're essentially removing that correlation. So that off diagonal terms should be going away by keeping just those approximations. It's not guaranteed, and we could have, maybe not filtered to the correct length or whatnot.
I think this is the tricky thing, because you're keeping the large scale structure, of course, which is
Yes.
correlated, but you don't care about that because it's not noisy.
Yes.
So it's the noise part of this, I guess, or
it's the small scale
the
stuff.
unresolved noise that you're trying to get rid of.
Yes.
Okay. That's helpful. Thank you.
No problem.
Any other questions or any other general comments about SWOT, inversion, assimilation, things people should know about, updates?
I'm going to stop sharing my screen.
And if not, let's thank Bradley again for a really nice talk and a good discussion.
Thank you.
Thank you very much, Bradley.
Thanks, everyone.